Yes, thank you for introduction, and thank you everyone for attending this session. So I'm Haruna from Obayashi Corporation, and I'm a lead researcher in Obayashi Corporation. Today we are presenting our challenge statement, robotic arm for confined space construction tasks. And today I have Andrew here, who will be also presenting together. Next slide, please.
Okay. Yep. So, hi everyone. I'll just kick off first and just give you a quick introduction to Obayashi to start. So some of you may know Obayashi. We've been in Singapore for 60 years. We just had our 60th anniversary a few weeks back. The company itself is over 133 years old now. Um, and obviously we're headquartered in Japan, where a large part of our business is. In terms of our innovation, we started off with Technology Research Institute in 1975. So that was also 60 years ago. So we've got a long history in R&D in the construction space. And over there, we continue to do R&D in all sorts of different areas. There's a lot related to earthquake-proof buildings, of course, being in Japan, but everything from sound to wind to materials. 3D printing, a very large range. We have over 200 researchers and 50 PhDs there. In 2017, we kicked off Silicon Valley Ventures and Laboratory. So we've been doing open innovation actively since then, and investing in some construction-related funds. And then in Asia, we started off in 2022 with a team called Asia Digital Lab. And last year we kind of spun that off and started up our business innovation team and our construction tech lab in Singapore, which is the organization myself and Harna work for. So we're actually part of Obayashi Corporation, and we report directly back into headquarters. But of course, we've got our Obayashi Singapore group company here. They're the ones who do all the hard work and the construction. You can see some of their projects there. Some of them you may be familiar with. Funan Mall, the Jewel development where you have the Andas Hotel, the Jewel at Changi Airport. And currently we're working on projects like the Terminal 5 substructure, a single cell comm center. We finished up Mandai Bird Park a little while back. So yeah, very active in kind of some landmark projects in Singapore. Okay, next slide, please. So I'll hand over to Harana now, who's going to explain more about our problem statement.
Yes, thank you, Andrew. So now I'm jumping to the actual challenge statement, and I'd like to start from some questions. Like, have you ever looked inside a manhole? And next slide, please. And have you ever even entered a manhole? And next slide, please. I think the space beneath a manhole is one of the toughest working environments on a construction site. And actually, I was shocked when I started my career in construction industry and watching workers go inside and working in a toughest environment. And I think, or we think, it is crucial to continuously and for this process, it is crucial to continuously monitor oxygen levels when personnel enter a manhole. And we, Obayashi, would really like to improve this work environment and thus presenting this challenge statement today. Next slide, please. So current process have a lot of problems. First, the physical strain. The workers face significant strain in non-standing positions while working beneath the manhole, and dust and fumes. Grinding and chipping produce health-risking dust and fumes. So typically, beneath the manhole, there's a pit, and it requires waterproofing process. And in order to move to waterproofing process, first we need to smoothen the surface of the concrete. And there, grinding and chipping take place, producing dust and fumes. And thirdly, volatile solvent emission. So waterproofing tasks release harmful volatile solvents. And oxygen level monitoring. So continuous monitoring is needed due to low oxygen risks. And finally, inadequate lighting. So poor visibility from temporary lighting increases accident risks. So these are current problems you are facing when working beneath the manhole. Next slide, please. So our challenge statement is, how might we automate construction tasks in confined spaces using a modular robotic arm that is capable of performing waterproofing, coating, and other surface preparation tasks? Next, please. So this is a brief overview of the current process. So we start from surface preparation, and then we apply primer and move to the first layer application and cloth application if necessary. Then second layer application to top coat protective mortar application if necessary. So the glade processes are optional for this BEAMP program. We are looking essentially at the pink portion, the primer application, first and second layer application of the waterproofing materials. So next is what kind of materials is used. So typically we use primer and we apply approximately 0.1 to 0.2 kilograms per square meters. And for first and second layer coating, we use approximately 1.0 to 2.0 kilograms per square meters. And for top coating, approximately 0.3 to 2.0 kilograms per square meters are used. And we use, according to the different materials, we use brush, roller, or trowel. And next slide, please. And here is a typical conventional inspection method during and after these processes. So first, we track the material usage. So first, we calculate amount of materials needed in kg as standard usage. So the number I previously mentioned, multiplied by actual construction quantity. So if we apply primer, which is required 0.1 kilograms per square meters, and we're doing it for 100 square meters, we will need 10 kilograms of the material. So we take photos of the used materials as evidence, like shown in the bottom, and this is how we track the material usage in a conventional process. And secondly, we use wet film thickness measurement. So there's a special gauge that is used for measuring the film thickness, and we apply a gauge to the wet surface and measure the film thickness from the height which the material adheres. So from there we can see the thickness, film thickness of the materials applied, and we make sure that it reaches the minimum required film thickness. And finally, we do pinhole inspections. The pinholes are some like micro holes, which you can see in the bottom photos. And we confirm the absence of pinholes through visual inspection or sensor-based methods. And the reason why we put these inspection methods here is that when automating and using robots for replacing the current conventional method, we're also looking to automate these inspection methods using robots as well. So preferably the application should consider how we can inspect the quality of the work done by robot using the robot. Next slide, please. And now moving on to the requirement. So for us, the most important requirement is that the robot can perform tasks without a person entering the confined space and access all 6 surfaces of a pit, measuring approximately 6 meters by 2 to 3 meters by 3 to 4 meters. And it is advisable to position the robot above the pit. However, this is not a requirement. So we are looking at the solutions robotic solutions that can address these waterproofing work beneath the manhole and without requiring personnel to enter inside the pit. And our recommendation is to place the robot on the slab, upper slab, because you'd like to cover the entire 6 surfaces of the pit, and it would be better if we place the robot outside the space so that it can reach all the faces. So that is our requirement. Next slide, please. And for POC and pilot, so initially we are thinking to conduct the POC by installing a mock-up at the BCA Bradell campus, where we have our office. And regarding the commercial viability of this program, first, tasks in confined spaces exist at all sites. So once this solution is ready to be applied on construction sites, the target site will be literally all the sites in the construction industry. And secondly, a robot that can work in confined spaces can also work in regular areas, which cannot be possible in a reverse way. So I think if one could address the robotic solution that can address these works in confined space, that robotic solution can be will be versatile and can be applied in regular areas. And we think there's a big potential market associated with these challenges in robotic solutions in confined space. Yes, that's all from Obayashi. Yes. Thank you.
Thank you, Haruna-san. Thank you, Andrew. All right, now would like to open the floor for questions. Please type in your question. I think meanwhile, Haruna-san, just want to probably post a question here. Have you tried any past solutions, and how did that go? Any learnings from there?
We haven't tested any solutions simply because there's no available solutions that can operate and do the actual tasks in this environment.
Got it. Got it. Thank you for that. We have a question from floor. So the first question is, are there any constraints in terms of weight and size of the robot?
If we are considering, so there's two ways. One is to actually place the robot inside the pit. In this case, the diameter of the manhole is typically 600 millimeters. So if you're looking at placing the robot beneath the manhole inside the pit, this 600 in diameter will be the constraint of the size. But if you're thinking about placing the robot outside the pit, there's not so much restrictions in terms of the size. But for the weight, I think typically these places are even below the underground floors. So this is placed at the very bottom of the building itself. So it is difficult to transport using the cranes or lifts. So it is advisable that this robotic solution can be transported by manually. It shouldn't be super heavy so that it requires a crane hoisting or lift. So that is the basic requirement in terms of the size and weight.
Right. Thank you, Haruna-san. Hope that answered your question, Elliot. Next, there's a question from Cecilia. Are universities included? I think as a solution provider, I think you may put in a submission, but eventually you need to show your plan to spin off. I think the funding can only go to an incorporated company eventually. So that's the response for that. Howie, must the solution be autonomous or remote operated?
It is preferable if the robot can work autonomously, but it's not mandatory. So I think so we don't want any personnel to inside the pit. So basically, we want the robots to either be autonomous or remote operated.
Got it. Thank you. Next couple of questions from Frank. Double check the requirement for installation must be able to perform outside the pit hole. Isn't that modular design is meant to break down the robot into small particle unit? So it's easier to mobilize into the pit hole and perform the installation inside the pit hole.
So majority of the robot is optional. Like if we have small enough robot, it doesn't need to be modular. If it's big, yes, there's some modularity will be required.
Cool. Next question. How does the waterproofing coating apply, roller or spraying?
So we either use a brush, roller, or trowel.
Got it. Next question. What are the sizes of most manholes?
600 mm for the diameter of the manhole.
Got it. Then next question, robot arm must be installed at the manhole entrance, or we can let one person go inside and install robot arm and base.
So we prefer not to let personnel go inside the pit. But for example, if we can consider like lowering the robot without person going inside the pit. So this approach is possible, but essentially we don't want personnel to go inside the pit.
Got it. Next question, prefer only robot arm or robot arm plus mobile base?
Either approach would be, I think, great. For us, the priority is eliminating the need for personnel to go inside, and depending on the size or reach of the robotic arm, it can be solely a robotic arm, or if the reach of the robotic arm is not like large enough, one can consider using the mobile robot together. So it depends on the size and specs of the robotic arm, I think. But we don't have any preference.
Got it. In addition to beams and manholes, is there any other type of obstacle?
Yes, but I think for this one, because this is PLC, we can start from the simple setting configuration. So at this point, we don't need to consider any other obstacles, I think.
Got it. And last question from Frank, can we fix some sensors on the wall?
Depending on the sensor, I guess.
All right. Hope that answered all your questions, Frank. Next from Jackson. Hi, would like to clarify how big is the opening of the confined space? I think this is already explained. It's 600 mm. Then next question from Cecilia. Did you consider soft robotic arms?
So I think solution can be like either industrial robotic arm or cobot or soft robotic arms. We don't restrict the types of the robot.
Yeah, hope that answered your question. Next question from Glenn, who's another CSO on the call. Are there any constraints in terms of the site condition blocked by a structure, beam, etc.?
Sometimes we see the beams, but I think we can start from the simpler configurations for the POC.
Got it. We have a next question from Elliot. What's the funding size and timeline? I think if I can sort of answer from the BEAMP perspective. So this is completely based on the proposal that you're going to put forth. The timeline will either fit the ASD or MD track that earlier was explained by Jiaming. And depending on the scope of the project, you will either go through a 6-month or 1.5-year timeline in execution. Both of this track have different funding range. ASD is 50,000, MD is 250,000 up to. So yeah, you may, I think, reasonably scope the pilot that you have in mind to solve this problem, and then we can see which track you fit the best. Next from Glenn as well. Can the robot be deployed inside the robot to move on its own rather than attached to a structure from outside the vehicle?
Yes, so we don't restrict the robot solutions. I thought both approaches possible. One thing we need to keep in mind is that we are applying the coating materials to all the surfaces of the pit. So if we deploy the robot inside the pit, the footprint of the robot cannot be painted. So we may need to have like 2 phases of the painting process, like robot. So in the first phase, robot is on the half places of the space, and then apply the coating on the other side. And then once the coating is dried, the robot moves to the other place so that it can cover the entire surface. So this will put additional process, but I think we don't restrict any robotic solutions. So either way is possible, but I think it is advisable to consider placing the robot outside the pit.
Cool. Thank you. Hope that answers your question, Glenn. And final question from Nish, Augmentus Robotics. Will there be CAD drawings for each pit hole before a robot is deployed?
Yes. So I think, yeah, if required, we can provide this example drawings as well.